All right. Greetings, YouTube. Beautiful Mind here. This is going to serve as we're going to continue our discussion on anti-differentiation / integration. This is going to be section 4.2 from our text. So let's hop on into it. Okay. Let's see. So this is chapter 4, section 4.2, antiderivatives as areas. And some objectives here, we want to find the area under a graph and use it to solve real-world problems. And we want to use rectangles to approximate the area under a graph. So with this example 1, so we have a vehicle travels 50 miles per hour for 2 hours. How far has the vehicle traveled, right? So, 50 miles per hour for 2 hours, 100 miles is not that difficult to get to. But let's see how the approach, right? So we treat the vehicle's velocity as a function. So v of x equals 50, right? You see it here. So the velocity is constant. We graph this function and sketch a vertical line at x equals 2 and obtain a rectangle. This rectangle measures two units horizontally and 50 units vertically. Its area is the distance the vehicle has traveled, right? So 2 hours times 50 miles per hour is going to give us 100 miles. So you can see that here. Okay. So the velocity of a moving object is given by the function here, where x is in hours and v is in miles per hour. Use geometry to find the area under the graph, which is the distance the object has traveled, right? During the first 3 hours, and then between the 3rd hour and the 5th hour. So this velocity is linear, right? So we would graph. I'm probably just going to use the prepared notes, the typed ones. We could graph it, but this would be a diagonal line passing through the origin with a slope of +3. So then we would want to find the area under the curve between as x goes from 0 to 3. So then it would make a right triangle, and then we can use 1/2 the base times the height. The base will be what, 3? And then the height when x is 3 is 9. So 9 times 3 is 27, so it should be 13.5, right? So I just use like 1/2 base times height. That one should be 13.5 miles. And then from 3 to 5, that one makes, it's just like a four-sided figure, but you can break it into like basic shapes. Actually, you can find the area of the larger triangle and then subtract the area of the smaller. Let's just kind of see it in action. So I think that the school might be on break right now, but I'm gonna go ahead and go with this lecture anyway, because this is just the next component. So again, for part A, the graph of the velocity function is shown at the right. Okay, so you see the diagonal line, and it makes a right triangle, and then I think we got that same 13.5 during the first 3 hours. So then if we want 3 to 5, we could just find the area of this triangle, right? So the height here, when x is 5, the speed is, what is it, 15? So 1/2 the base times the height, 5 times 15 is what, 50 plus 25 is 75? And then half of that, 35, 36, 37.5. So the big area, the big triangle will be 37.5, and then we will subtract the 13.5. 37 minus 13, 37, 27, 24. So then the remaining area of this region here should be 24 miles. So you see here. Now they decided to break it into the simple shapes, right? They found the area, so it's like, basically we're talking about this region here. So it's two simple shapes. You have a rectangle and you have another right triangle, right? Did we get 18? We might not have. But I mean, also we were doing it in our head, but if we write it out, I think it'll be fine. Now I'm intrigued. Let me see, make sure that what we did before was fine. 5 times 15, 50 plus 25 is 75. And then 75, if it was 7, it would be 35, 36, 37.5. Right? 37.5 minus 13.5. 37 minus 13, 27. Am I cutting in half? 27. I got 24. And I got 18. Now I'm not sure what I'm doing wrong. But basically, I just was doing the, let's see, 1/2 the base times the height, 5. Let me see. Hey Siri, what's 5 times 15?
5 times 15 is 75.
Hey Siri, what's that answer divided by 2?
75 divided by 2 is 37.5.
Hey Siri, what's that answer minus 13.5?
37.5 minus 13.5 is 24.
How am I getting a different result? $30 is 15. Oh, wait a minute. Oh, no. I think I'm just trying to move too fast. Let me try something here really quickly. 9, 18. Let's see. 3 times 3 is 9. Times 3 is 27. 13.5. It should be the case that those two added together. Okay, let me confirm what they're doing. That's definitely 2. Right here, when x is 3, 3 times 3 is 9. So that looks good. So if that's 9, that's 15. So then it has to be 6. Oh, okay. Maybe I need to keep going. Oh, duh. Okay, yeah, it was driving me nuts. I was like, why are we getting different results? It should be the same. We actually do. I just need to go to the next slide. Because I wasn't paying attention to what they were doing. The 18 was only the area of the rectangle. Then they went and found the area of the triangle, and then they added the two together, and we got the same result. I think we got 24. I felt like I need to do it again. But again, just trying to move too fast. But anyway, I was like, that's irking me. It was irking the hell out of me. But anyway. Yeah, so we got the same thing. I just, again, I didn't realize that I just needed to keep going because they added the two areas together. But yeah, so we got the same thing, okay? I usually leave this as an exercise. Okay, so we're going to kind of move forward there. So then we have this notion of what do we mean by Riemann sums. So the last two examples, the area function is an antiderivative of the function generated that the last two examples, the area function is an antiderivative of the function that generated the graph. Is this always true? Is the formula for the area under the graph of any function the antiderivative of that function? How do we handle curved graphs for which the area formulas may not be known? We investigate the question using geometry in a procedure called Riemann summation. So remember, uh, with section 4.1, we introduced this notion of antiderivatives. It's like given a function, if you take the derivative, or with antiderivatives, given a derivative, how do we get back to the original function? So we explored some ways of doing that. So then in a graphical sense, we're exploring this idea that the area under the curve gives us the antiderivative of a function. Okay, and we're gonna explore finding the area under the curves using this concept called Riemann summation. Okay, so in the following figure, the closed interval from A to B, so here's A, here's B, is divided into 4 subintervals. All right, so we broke that into 4 equal intervals, each having a width of B minus A over 4. So they took the total distances divided by 4, and that's the width of each subinterval. The heights of the rectangle are f of x1, x2, x3, and x4. So the height is, we're using the left corner of each rectangle. We could base the heights based on the midpoint of each subinterval. We could also do it based on the right endpoint of each subinterval. Okay, but for this one, we're using the left corner or the left endpoint of each subinterval to find the height of the rectangle. Okay, so then the area of the region of the curve is approximately the sum of the areas of the 4 rectangles, right? So if we want the area under this curve as x goes from A to B, we can use these rectangles to approximate the area. It's not going to be exact because you have gaps, right? There's a gap there, there's a little bit more there, less there, right? So it is safe to say that the smaller the subintervals, the better the approximation of the area under the curve. So the area of the region under the curve is approximately the sum of the areas of the 4 rectangles. So area is what? Length times width. So the length times the height plus the length times the height plus length times the height, length times the height. We can denote this sum with summation or sigma notation. The Greek capital letter sigma is here. The symbol just means add up your results, right? Summation, or, it means add them up, right? So this is read the sum. This is read the sum as I goes from 1 to 4 of f of x sub I delta I. And so this subscript is just, so basically this means like, okay, you start, let I be 1 first. So you're going to say f of x sub 1 times delta x. Then you say plus, now let I be 2. F of x sub 2 delta x plus f of x sub 3 delta x. You keep going until you get to I is 4. Let me see, what's the difference between these? Okay, so we can put the summations on top and bottom or off to the side, but they mean the same thing. Again, this is read the sum of the product f of x sub I delta x as I goes from 1 to 4. To recover the original expression, we substitute the numbers 1 through 4 successfully for I in this f of x sub I delta x and write plus signs between the results. And okay, well, they didn't show it, but that's okay. So we're asked to write the summation notation for this. Okay, let's give it a go before we look at the result. So we are adding up our results. It looks like we're adding up I as I goes from where? No, it's not that, because I was going to say from 2 to 10, but then that would include 3 and so on and so on. These are all, this is like 2 times 1, 2 times 2, 2 times 3. So we're going to augment this. We're going to say 2i. as I goes from 1 to 5. Okay, let's write this out. So this would be 2 times 1 plus 2 times 2 plus 2 times 3, 2 times 4, and 2 times 5. That's what the notation means, right? And then I think we get what we want. 2 plus 4 plus 6 plus 8 plus 10. Okay? So then this is the summation notation. So this is a tangent. I keep trying to watch Kong or Godzilla versus Kong, and I keep falling asleep on it. It just seems like, I don't know. Anyway, I should have did spoiler alert. And it's not a bad movie. It's nothing like that. I don't know what's going on. It's raining here, so I don't know. That might have something to do with it. But I just be like, I just cannot stay awake. I've tried like maybe 3 times consecutively. I tried to watch it as soon as I wake up, but I struggle watching movies. So it has nothing. It speaks to nothing about the movie. It's just I struggle to watch movies at this stage of my life. All right, I think this is what we got, right? So note that we are adding consecutive values of 2. So then as I goes from 1 to 5, so the sum as I goes from 1 to 5 of 2i. Okay, let's try another one. I usually leave the quick checks as an exercise, so I'm going to leave those for you. Write the summation notation for this. Okay, what's changing? Only the subscripts on the x's are changing. Everything else is staying the same. So what we're doing, this should be the sum as I goes from 1 to 19. We got g of x sub I delta x, all right? So then if we were to expand the summation, the first one would be g of x sub 1 delta x, you see it here, plus g of x sub 2 delta x, you see it here, and you would keep going until you get to g of x sub 19. So this should be it. But it's, I mean, I enjoy the movie. I just could not stay awake. Anyway, okay, I think that's what we got. As I goes from 1 to 19, g of x sub I delta x. Okay. Express this without using summation notation. Okay. So let's start. I don't know. Even though the original is right there, I still like to write a copy. As I goes from 1 to 4, we have 3 to the power of I. Okay. So let's expand this out. So first, let I be 1. So this is going to be 3 to the power of 1 plus the next one. And now I is going to be 2. 3 to the power of 2 plus the next one. We keep going until I becomes 4. So we're going to say 3 to the power of 3 plus 3 to the power of 4. 27 and 81. Okay, let's keep going. 3 plus 9 plus 27 plus 81. Let me see. These two together make 90. 100, 110. So then if we add in this, it's going to make it 117. So then 120. All right, looks like it's 120. We're going to go with that. Okay. You see it there. Okay. So express this without using summation notation. Okay. So you see the I, the only thing that's changing is I. Oh, okay. So now notice it's like, what, 30 expressions? We're not going to write all 30. So we're just going to write the first couple. So let me see. The first one will be h of x sub 1 delta x plus h of x sub 2 times delta x. And then we continue the pattern until we get to h of x sub 30 times delta x. Right? That's how we would write that. So again, these ellipses just mean continue the pattern. You know, you write the first few of the pattern and then continue that pattern until you get and you stop when x is 30. I mean the subscript is 30. You see it here. Okay. So consider the graph of this over the interval 0 to 600. Approximate the area by dividing the interval into 6 subintervals, and approximate the area by dividing the interval into 12 subintervals. Let's see. So what is this? An inverted parabola? I think I'm just going to use the typo. I mean, we could graph it, right? Because we have the vertex. And then if we divide it into 6 subintervals, I mean, it's a little bit of work. I'm going to start it. I don't know that I'm going to finish it because it does get a little bit involved. Let's see. Let's go paper. Let me add another page. Okay. So then we have f of x equals 600x minus x squared, right? So it's a parabola, right? Let's just graph it. Let's see the vertex. Let's start with the vertex. So our h is negative b over 2a. That's the x coordinate of the vertex. Let's see. So that's going to be negative 600 over 2 times negative 1, 300. All right. So then the k, which is the y coordinate of the vertex, which is going to be f of h. So that's going to be 600 times 300 minus 300 squared. 18 minus 9, is that right? 6 times 3 is 18, what? 180. 180, 1, 2, 3, minus 9, 1, 2, 3, 4, equals 90. Okay. I'm going to do a rough sketch. Now we said as x goes over the interval from 0 to 600. Let's see, if we plug in 600, I think we're back at 0, right? And it looks like the max occurs at 90,000. I'm just trying to think. Okay, so like say this was the origin. Let's go, let me see. That could be 1, 2, 3, 4, 5, 6. Okay. So the x-axis is just x. So this is the positive x. Now we can go maybe up to 10. Let's go like this. Let me see. 1, 2, 3, 4, 5, 6, 7, 8, 9. And we need a little bit more space. One, 2, 3, 4, 5, 6, 7, 8, 9, 10. That'll be our positive. I'll just say, yeah, we'll call it f of x. Let's see, x's, we went to where? 0 to 600. So we can let, this can be 0. We said this was what, 100, 200, 300, 400, 500, 600. Okay. And then on the y-axis, we're going to say, I'm going to do a shorthand. This is going to be in what? We'll say in 10,000s. Okay. So this should be 10,000, 20,000, 30,000, 40,000, 50, 60, 70, 80, 90, 100,000. Okay. So now we got the vertex occurred 390,000. So if we go over 300 and up to 90, let's do it like this. Let's go paper. some reason it's a little bit easier like this. So 390 is here. Okay. We probably could plot a few more points to get a better graph. Yeah, let's plot points. Let's find the corresponding y for each x. Probably my calculator would be easier, but I'm going to use Siri. Let's see. Hey Siri, what's 600 times 100 minus 100 times 100?
600
It's
times
50.
100 minus 100 times 100 is 50,000.
Okay, this is where like the calculator would be a lot faster. Hey Siri, what's 600 times 200 minus 200 times 200?
600
80.
times 200 minus 200 times 200 is 80,000.
Okay, I think we can use symmetry. So I'm just going to assume for right now, when it's 4, we should get 80. 1, 2, 3, 4, 5. Wait a minute, something's not right. 1, 2. Oh, 5. Yeah, 5 should be 5. Right here it looks like. And then that should be back to 0. Okay. So then we should get something that looks like this. And what I'm going to do, what happened? Let's undo that. Try that one more time. It looks pretty good actually. Wow. Okay. Now let's go style. We want to thicken it up just a little bit. That looks good. Okay. So this is the graph that we got. Now we're actually divided into the first for part A. The axis is divided into subintervals. So let me. I want to copy and I'm gonna paste. So I just made a copy of the work that we did. Okay. Because we have two different. So I'll label this as part A. We'll do it in green. So 6 subintervals, right? So we have the one on the left. Let me see. 1, 2, 3, 4, 5, 6. So we're going to use the left corner like before, right? So we have this first subinterval. Then we have one from here. Okay. Let's see. I'm going to just let me do the following. So we have from here to here. Okay. Just kind of bear with me for a moment. Like that. So again, I'm going to use the left endpoint to calculate my heights. Okay. So let's see. Let's do like this. Style. Let's go there. Okay. So then this one, style. It goes this one. And actually, we can copy that and let's paste. Okay. So there's the second one. I'm gonna just go ahead and paste. The third one based on the left, paste, based on the left, paste, based on the left, and paste. And then what we need to do, style, like that. That one's fine. Like that. That one looks good. Let's copy. We're going to paste that right there. Basically like that. We can just paste the same thing. So we're going to paste. It will go here, and we'll do like that. And then paste. This one will go here, like this. Okay. So now so all of these heights, we did it based on the left endpoint, right? So now we have 1, 2, 3, 4, 5, 6 rectangles. So if we go back, we're asked to approximate the area by dividing the interval into 6 subintervals. Okay. So then what's the area? What's the area of the first rectangle, right? The area is 0 because it has a height of 0. So let me see, the length is what, 100? So we're going to say, I'm just going to call it A for now. The area is going to be what? the length base times the height, right? So 100 times 0, so you know what happens there. The next one is going to be 100 times that height there is what, 50? 50, 1, 2, 3. I'm going to just use ellipses for now to continue the pattern. And the last one is going to be 100 times, I think that was also 50. I should write it all the way out. I'm just not going to do that. So then the first area was 0. The second one, that's a 5 with 4 and 2 is 6 zeros. 1, 2, 3, 4, 5, 6. 5 million, okay. The next one is going to be what? 8 with 6 zeros. 1, 2, 3, 4, 5, 6. Okay. This one is going to be what? 9. I think we said it was 90. So that's a 9 million. Let me see. Then it should be symmetric, right? So that's 9, 8, 5, and 0. So just for the sake of space and time, I'm just going to put times 2 for each of those. So I'm going to say like times 2, this one times 2, that one times 2, and not the last one. Okay. So then that's what, 10 million, 16. Let's do this. Hey Siri. Oh, wait a minute. Wait a minute. 1, 2, 3, 4, 5. I think we're okay. 1, 2, 3, 4, 5, 6. Okay. 10, 16, and 9. Hey Siri, what's 10 million plus 16 million plus 9 million?
On it. 10 billion plus 16 billion plus
Nope.
9 billion is 35 billion.
35 million. Okay. For some reason she heard billion. 35. 1, 2, 3, 4, 5, 6. Okay, let's see. So we got this result. Let's go ahead and do part B before we look at the final result. So part B essentially asks us to do the same thing, but instead of 6 subintervals, we want 12 subintervals. So like I said, I made a copy of the work that we did, and we're going to work with this one, this graph, right? Okay. And we'll do this one. Let's do, I guess we could do orange. This will be part B. Okay. So if we're using the left, let me see. So we would do one from there. Well, we still have all the same original ones. So let's go style. I think we were doing about that thickness. Let's copy, paste. So I'm just putting the originals there first. Okay. So these are the 6 subintervals, but then like the half. When x is 50, what's that y value? I'm just curious. So 50. Hey Siri, what's 600 times 50 minus 50 times 50?
600 times
27,500.
is
Okay.
27,500.
Paste. So like for instance, this one should be 27.5, so it should like be about right there. We'll just go with it. Ugh. Okay, let's just go with it. Keep going. So we need all of these half marks. Okay. All right. So then if we're using the left endpoint like we did in the previous, so let's do now before. Okay, so the left one would be there. The left one would be there. And that triangle's formed. I mean, that rectangle's formed. The left one is here. The left one is here. In hindsight, I'm feeling like I probably should have used the prepared notes for this, but I just got carried away. Like, it's just fun. So we want to paste. The left one is there. We'll come back and connect those momentarily. The left one is here. The left one is here. The left one is there. Here. And here. All right. And then we just want to like go like that. Something is off there. Okay, that'll do. And then this one, and I think we need one more. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So let's copy, paste. Okay. Okay, so we created the 12 subintervals, then we would have to find the area of each of those. Looks like we have the whole symmetry thing going on again, to a degree. Let me see. 1, 2, 3, 4. Let me see. There's not two of the zeros, but that didn't matter. But there were definitely two of these and two of those, one of those and one of those. So I think that one was fine. Let me get rid of this extra two because we didn't have two of the zeros. So this area should be what, 0? We're going to have two of this one, so that width is what, 50? What's this? Let me see. If we plug what is this one? When x is 50, what's the y? Let's see. Hey Siri, what's 600 times 50 minus 50 times 50?
600
27,500.
times 50 is 27,500.
And the width is 50. Okay. Yeah, I don't feel like calculating all those. But basically, I mean, I think you get it. Find the area of each rectangle and add up your areas. I'm just not going to do it right now. Okay. Let me see how many. 1, 2, 3, 4, 5. Those are all duplicates. So I'm just going to go ahead. I know this one is times 2, so I'm just multiply that one times 2. When x is 100, let's see. It's like that's a 50,000. I'm still trying to just do it. I know this one's going to be times 2 because it occurs twice. The width is 50 and the height is what? When x is 100, y is 50,000. Okay. Then we could say plus, it should be 2 times 50. Now when x is 150. No, what happened? When x is 150. Hey Siri, what's 600 times 150 minus 150 times 150?
600 times 150 minus 150 times 150 is 67,500.
Okay. So I know there's two of those. At the 200, I'm just going to kind of keep going here. It should still be times 2 because that one should occur twice. The width is 50 and the height at 200 looks like it's 80,000. See the previous, that looks good. So we did the 200, we're almost there. I think this is the last double at 250, right? So 2 times 50 when x is 250. Hey Siri, what's 600 times 250 minus 250 times 250?
600 times 250 minus 250 times 250 is 87,500.
Okay. That's the last double. We should have 5 of them. 1, 2, 3, 4, 5. And then the last one is not a double, which is the 300. So that width, that one doesn't occur twice, but the width is 50 and the height, I think, was 90,000. Okay, we have to calculate all that. I think I am going to use Siri, so I'll try it no more than twice. I should be able to get it on the first one. Okay. Hey Siri, what's 2 times 27,500 times 50 plus 2 times 50? Cancel, cancel, cancel.
2 times
Yeah, I was
27,500
trying to get her not to do it.
times
Because instead of saying 2 times 50, I'm going to just say 100. All right? Okay, let's try this again. Well, we could just simplify it ourselves because 100 times that is easy. I just want to get to the answer. Hey Siri, what's 100 times 27,500 plus 100 times 50,000 plus 100 times 67,500 plus 100 times 80,000 plus 100 times 87,500 plus 50 times 90,000?
100 times 27,500 plus 100 times 50,000 plus 100 times 67,500 plus 100 times 80,000 plus 100 times 80. 7,500 plus 50 times 90,000 is 35,750,000.
Is that close? Yeah, and that's close to the other one. The whole point is that it was supposed to be close. The other one was 35 million. This one was 35,750,000. So this should be a better approximation because we took smaller subintervals. I know I said one a little different. Let me check something real quick. It's this one, the second to last one. So not at 300, but at 250. I want to recalculate that one. That should be at 87,500. Let me see, when x is 250. Hey Siri, what's 600 times 250 minus 250 times 250?
600 times 250
Yeah.
minus 250 times 250 is 87,500.
So I think I had 87,000 even. That's supposed to be 87,500. Okay, but I know when I calculated the last one, I said 87,500. Okay, I'm gonna go with this, right? So let me do some housekeeping here. I would like, but I think you can see like with the time it took me to like do this by hand, why I was like I wanted to skip it, but it's okay. I couldn't help myself. Let's get rid of this, and okay, that's us doing it there. Let's go back to view, single page. Okay, let me see my time. The time is, okay, we still got a solid 30 minutes. Okay. So we got 35 million for the first one, and we got 35,750,000 for the second. Okay. So 600 minus 0 divided by 6 was 100. So the delta x was 100 for each one. So 0, Okay, I think we did all this. That looks okay. So you see the graph was the same thing that we got. 35 million. That's exactly what we got. And then into 12, so each one was 50. And 550 was the last one. And the total area you see there is a 35,750,000. It's pretty cool. You see it here. Okay. Oh, I thought they were going to go into an analysis. But yeah, that was it. That wasn't too bad. Okay. That was fun. So then we have a section summary. The area under the curve can often be interpreted as in a meaningful way. The units of the area are found by multiplying the units of the input variable by the units of the output variable. It's crucial that the units are consistent. Geometry can be used to find the areas of regions formed by graphs of linear functions. A Riemann sum uses rectangles to approximate the area under a curve. The more rectangles, the better the approximation. The indefinite integral, the integral from a to b of f of x dx, is a representation of the exact area under the graph of a continuous function, where f of x is non-negative over a closed interval from a to b. Okay, that was fun. I think the most fun part was like graphing, like drawing the graphs. Right, I always enjoy that. I'm actually an artiste. Okay, so hopefully that was okay for you. And on that note, we're going to end the session here. And from one beautiful mind to another, enjoy the rest of your day. Peace.